So we'll do an example of a 3-month Asian option where we'll take 1-month step sizes. So we'll imagine that this is an arithmetic Asian option. Recall there are 2 types, arithmetic and geometric. This is an arithmetic, and it's a monthly arithmetic, meaning the payoff function depends on the average of 3 monthly stock prices. Of course, it doesn't reflect as 0 because that's known. It reflects the prices at time 1 month, 2 months, and 3 months. So notice that how we are successively generating the stock price at time 1 month, 2 months, and 3 months using the procedure, the path procedure that was introduced earlier. We generate 3 random normals, and each one of them gives us a path. Each path then gives us an Asian payoff. We average the 3 prices and compare it to K. And we can then repeat this exercise using every time we generate 3 random normals, we generate an Asian payoff. We can then calculate an average of these by repeating this exercise 2,500 times or 1,000 times. We can then generate 1,000 Asian payoffs, take an average, and we've got our Monte Carlo estimate of this arithmetic Asian option. We can do exactly the same procedure for a geometric option. The difference, of course, is that instead of the payoff function being an average, it's a geometric average. It's not arithmetic, it's geometric. The interesting thing is, even though a geometric option is a somewhat more complicated calculation than a simple average, it turns out that the form of this works very well with the log normal distribution, and that you can, there are exact formulas like the Black-Scholes formula for evaluating geometric Asians. So even though it looks like a more complicated exercise function, you can actually write down an exact formula for a geometric Asian option, whereby an arithmetic Asian requires numerical simulation. And that's an important observation, as we will see. So here's a table of values that is in the chapter, table 19.3. And it shows you the number of paths that went into the averaging. And so, you can generate 1 path of prices, and excuse me. And so there are 10,000 trials. So each one of the prices uses 10,000 trials. Now, one of the complexities of an Asian option is that it's a 3-month Asian option, and the question really becomes how many average prices go into the averaging. And there are some Asian options that are defined, it can be defined as weekly average, in which case you would only want to capture the prices weekly. Some Asian options use the average of daily prices. So what's going on here is this is the number of averaging. Remember, this is a 3-month option, and so how many prices are being averaged? So we can average 1 price, 3, 5, 10. If we average 1 price, that's basically a European option, and then we average more and more prices. We averaged 3 prices in the example I just showed. And in each one of these, the author is using 10,000 trials. So whether we average 3 prices, we'll generate 10,000 paths where we average 3 prices, and we get a Monte Carlo arithmetic price, a Monte Carlo geometric price. We can also do 10,000 paths where we take 5 steps to get to expiry instead of 3, or 40 steps. And you can see that the prices appear to be converging, that as we sample more and more prices in the average, we're capturing more and more of the total price volatility. Notice that there's an exact geometric price column. There's no exact arithmetic price column because there's no formula for that. There is a formula for exact geometric. And then here, this is the sigma, the standard error of the estimate. And of course, in each one of these cases, this is going to represent, by the formula we had, sigma c over the square root of 10,000. Sigma c being, if I look at the standard deviation of the 10,000 individual Asian payoffs. And notice that the standard error is dropping as I sample more and more. So you'll also notice that the arithmetic prices for a call are greater than the geometric prices, and this is an application of Jensen's inequality, namely that the arithmetic average always is bigger than the geometric. You probably know this from first principles, but this is really related to Jensen's. Because what Jensen's inequality says is that the expected value of f of x is going to be smaller than f of the expected value of s if I have concavity, if f is concave. If f is convex, it goes the other way. So here, the function we're interested in is log x, concave. And so what Jensen's would say is that the expected value of a sample of log, say, xj, is smaller than the log of the expected value of xj. And so if I just assume a random sample of x's, the expected value of the log of xj is 1 over n times the summation of the log of xj. And that's smaller than the log of the average. And if I just exponentiate both sides, by doing exponentiation, this becomes the geometric and this becomes the arithmetic. So the fact that the arithmetic exceeds the geometric is a function of the Jensen inequality, or a byproduct of the Jensen inequality. And because the arithmetic average is bigger, the value of an arithmetic Asian call will be bigger than a geometric Asian call. Reverse is true for puts. Arithmetic averages always are bigger than geometric averages. So if it's an arithmetic put, having a bigger average is a bad thing. So in fact, if you're dealing with puts, you would expect the geometric average Asian put to have more value, because geometric averages are smaller, and that's good for puts.